Hello everyone, I'm Pawel Gawrychowski, and this is joint work with Shay, Mozes, and Oren Weimann about a faster algorithm for the minimum cut problem. In this problem, we are given an undirected edge-weighted graph G. I will assume that the weights are integers, and we seek a partition of the set of the nodes into non-empty S and its non-empty complement. The goal is to minimize the total weight of all edges with one endpoint in S and the other endpoint not in S. These are the blue edges in the figure. This is a very basic question, and I'm sure you have all seen before, so I can skip the motivation part. Let me just say that because the question is very basic, we'd like to fully understand its time complexity. It's not hard to see that this problem can be solved in polynomial time. Basically, you only need to run a maximum flow computation between every pair of the nodes in the graph. And actually, when you think about it, you only need n-1 such computations. So by plugging in the fastest known maximum flow algorithm that works in n times m time, you can design an algorithm that works in n squared times m time. This is polynomial, but quite high. So is there a faster algorithm? Yes, Hauer and Oren show that, roughly speaking, a single maximum flow computation is enough if you use the appropriate maximum flow algorithm. By doing so, they were able to obtain an algorithm that solves this problem in m times n times log time. A completely different approach was designed by Nagamochi and Ibaraki. They showed that in m plus n log n time, we can either find the global minimum cut or isolate an edge that doesn't cross it. In the former case, we are already done. In the latter case, we can contract this edge and repeat the reasoning. So the graph will keep shrinking. There will be at most n iterations, and the overall running time becomes m times n plus n squared log n time. This idea of contracting edges has been then pushed even further by first Karger and then Karger and Stein. They used randomization to choose which edge should be contracted, together with some careful recursion approach. And this allowed them to find the global minimum cut in n squared times log to the power of 3n time with high probability. This is great when your graph is dense, but if the graph is sparse when m is roughly n, you only have a quadratic time bound. So is there something faster for the case of sparse graphs? In '96, Karger gave a different algorithm that works in the m times log to the power of 3n time, and again with high probability, finds the minimum cut in the graph. His idea was to reduce the problem to log n independent instances of a more structured question. In this more structured question, you are given some kind of a hint about the minimum cut, and this hint is simply a 3t. You are promised that exactly k edges of t cross the cut. And actually, either k is equal to 1, so there is one edge e of t that determine the cut, or there are two edges e and t prime of t, and together they determine the cut. So we call those cases the one respecting and the two respecting case. Okay, but how do you find such a hint? This goes back to an old theorem by Nash-Williams, who showed that if you have an unweighted graph with minimum cut C, then there is a set of C over 2 edge disjoint spanning trees in this graph. Now, by a simple calculation, because we have C over 2 edge disjoint trees and the minimum cut is C, then the average number of edges from the minimum cut per tree is 2, so the minimum cut 1 or 2 respects one of those trees, and you can use one of those trees as a hint. This is nice, but not straightforward to apply, because first of all, we want weighted graphs. Then C might be large, so even if you have those trees, then there is not enough time to look at all of them. And finally, we need an efficient algorithm that finds the minimum 1 and 2 respecting cut. So there are some obstacles that have to be overcome, but Karger was able to do that. And his first step was to consider weighted tree packing. This is just a set of spanning trees, each with its weight. And we want the total weight to be as large as possible under the following constraint. If you look at an edge of the graph, then the total weight of all trees in the packing that use this edge is at most the weight of the edge. So you want to pack as much as possible under these constraints. And then his approach to find t was as follows. First, he showed that in m plus n log n time, we can find an unweighted graph H with very few edges, only n log n edges, and small minimum cut bounded by log n that still captures some information about the minimum cut in G up to constant factor. Then he showed that we can apply the algorithm of plotting Shumoy-Stardosh to approximate the weighted tree packing in H. And the weight found by this algorithm will be sufficiently high. This takes n log to the power of 3n time. And the final step in his reasoning was that the fraction of the total weight of all trees in the found packing, 1 or 2 respected by the minimum cut, must be constant. So you can sample using those weights as probabilities, and with constant probability, you will hit a tree that can be used as a hint. This needs to be amplified by repeating log n time to obtain an algorithm that works with high probability. Okay, so this is how you find this hint. So now it remains to show how to find the minimum 1 respecting and 2 respecting cut, given t. For the 1 respecting case, Karger showed that this is actually quite simple. So this is the situation. You want to find HE that minimizes the sum of weights of all these green edges. So when you look at it the other way around, for each edge of the graph, so this is our edge UV, its weight should contribute to the answers to all edges on the path connecting U and V in T. So you can split this path into 2 parts. At the LCA, you can find the LCA constant time, and then basically you have to propagate this information on paths that go up. So this it's a bottom-up computation on the tree. This can be done in overall all of m time. So it's m to first prepare the information and then n to propagate. Okay, so 1 respecting case is easy. What about the 2 respecting case? So Karger observed that there are 2 cases. The edges E and T prime that we seek can be either independent, like that, or descendant, like that. He used different names, but anyway. So for both cases, his algorithm is very similar. It operates in log n phases. Each phase contracts paths that consist of nodes with exactly 1 child ending at a leaf. He calls them boughs. Each phase is implemented with a linked tree in m log n time. So the overall running time is m log² n time. Okay. In the full version of the paper, he actually suggested that there might be a way to decrease this time complexity for the finding the minimum 2 respecting cut. And his first suggestion was that actually we use linked trees, but all the operations are known in advance. So we are using dynamic trees, but it's really a static problem. So maybe this can be somehow exploited. And his second suggestion was that this decomposition into boughs maybe can be somehow tweaked, so there are fewer phases. Okay, so he gave these suggestions, but no one was able to use them. So no one succeeded in decreasing this m log² n time for the 2 respecting case. I should mention though that there was some very nice development for the simple unweighted graphs. So first of all, Hensinger, Rao, and Wang gave a faster deterministic algorithm for this case. Essentially, they shaped 1 log. And later, Gafari, Nowicki, and Torp gave even faster algorithm for this case. This one is randomized though. So we have some nice progress on the simple unweighted graphs. And very recently, there was a paper that shows a different take on the 2 respecting problem by Lovatt and Sandlund. Instead of linked trees, they used top trees. This is some kind of structure that I'm not going to define. And instead of using these bows, they iterate over the edges of T using the heavy light decomposition, which is a very standard definition in this context. So the algorithm is much simpler, but the running time is the same, m log²n. Nevertheless, this got us interested in this question. And our main technical contribution is a deterministic m log n time solution for the two-respect problem. So we show one log. This is not enough to obtain an improvement on the overall running time because there is this sampling step. And Karger only showed how to sample in m plus n log to the power of 3n time. So this is not necessarily an improvement if we can shave one log from the two-respecting problem. However, we showed the sampling can be implemented differently with weak his implementation actually, and then the running time becomes m log²n. And the overall running time is just the sum of those two, so m log²n. I should also mention that independent of our result, there was another paper that showed how to solve the two-respecting problem in m log n plus n log to the power of 3n. However, this algorithm is randomized, and it's not always an improvement on Karger's bound because of this n log to the power of 3n. Our method is deterministic, and it's always an improvement. Okay, so I will first show you how we change the sampling. So we follow the idea of Karger. The first step is to find an approximation of the minimum cut C. So we use a known algorithm for that, but we need to show how to implement it efficiently in the m log² time. Then edges with weight larger than C can be contracted without changing the minimum cut. And the remaining edges are treated as a bunch of parallel unweighted edges. We sample these unweighted edges with appropriately chosen probability, and this gives us graph H with small minimum cut. And again, we have to show how to implement this sampling efficiently in m log² time. So finally, we apply the following algorithm given by Young. It's a packing algorithm that operates on H. So initially, the cost of every H is 0, and we proceed in iterations. In every iteration, we find the MST using the current costs. We add the found tree to a collection of trees, and we increase the cost of every edge belonging to this tree by the cost of the tree. And then we repeat this whole process. Because of the properties of H, the number of iterations of the process is only log²n, and the single iteration is essentially an MST computation. This takes all of m time randomized. There are some small details here that I'm hiding, but this is the basic idea. Okay, so from now on, we can assume that in m log²n time, we have found a collection of log n trees such that the minimum cut 1 or 2 respects one of those trees. So we take one tree Ti, and we do the following. First, we find the minimum 1 respecting cut using Karger's algorithm in all of m time. Then we have to find the minimum 2 respecting cut defined by the dependent edges. So we show how to do this in m log n time, but it's not the main technical part. Then to deal with the case of independent edges, we introduce a new problem that I will define soon. And we show how to obtain a number of instances of this new problem in m log n time, and the overall size of all those instances is O of m. And finally, we show how to solve this new problem in time s log s, where s is the size of the instance. So this is the main technical part. Overall, it's m log² as promised. So how to deal with the case of dependent edges? We use linked trees. They implement many operations, in particular the following operations in log n time. You can add delta to the score of every edge in a path, and you can also find the edge with the smallest score in a subtree. So this is the update and query. We take T, this is our hint, and we binarize it, and then we sweep over the edges while maintaining the scores in a linked tree. And the idea is that when we encounter edge E, then we want the scores in the linked tree to be such that the following holds. For each edge E prime in the subtree of E, the weight of a cat defined by E and E prime is equal to the current score of E prime from the linked tree plus the total weight of all edges with exactly one endpoint in the subtree of E. And it turns out that you can maintain this invariant while sweeping over the edges. The number of updates to the linked tree will be 2 per edge of the graph, so O of M, and the number of queries will be 1 per edge of T, so O of M. So this is quite efficient. Okay, so now I have to define this new problem. We call it the Bipartite problem. We are given 2 trees and a number of cross edges that connect nodes with different trees. The goal is to find edge E and E prime that minimize the sum of the costs, so each edge has a cost, minus the total weight of all cross edges connecting the subtree of E with the subtree of E prime, so those green edges. Okay, so recall that we are in the case of independent edges, so we seek E and E prime that look like that. Let's think about the LCA and call it X. We will have a separate instance for every node of T, so in particular we have an instance of the new problem for X. And somehow this instance should be responsible for finding E and E prime. So let's think about the weight of a cat defined by E and E prime. So it's the total weight of all edges with one endpoint in the subtree of E plus the total weight of all edges with one endpoint in the subtree of E prime. And now we have to subtract the total weight of all edges connecting the subtree of E with the subtree of E prime. So this is exactly the Bipartite problem. So you can see the connection. However, there is an issue here. We have very few instances, 1 per node of T, but in many of them, we might have large subtrees. So how to deal with that? Well, let S be the number of edges, UV, with the LCA equal to X. So now it turns out that even though the subtrees might be very large, you can always kind of compress them because only O of S edges really matter. And this is because of the following. So let's think about one of those trees. The green nodes are the endpoints of the cross edges, and take the subtree induced by those green nodes. Now, when you have a long path in the induced subtree, and there are no green nodes on this path, then actually you only want to keep the cheapest edge from this path. Only this edge is possibly interesting. So with path minimum queries, this allows us to kind of compress the tree to consist of at most 2s edges in s log n time. So that's the main trick in the reduction. Okay, so from now on, we can focus on the Bipartite problem. So we are given T1 and T2, and the goal is to find for each edge E of T1, the cheapest edge E prime of T2. So we will apply divide and conquer, guided by the heavy light decomposition of T1. So in every step of the recursion, we'll have a fragment of T1. A fragment is a subtree rooted at some node U1, possibly without the subtree rooted at some of the node UK, the subtree of U1. So initially, we have the whole tree. This is also a fragment. Every subtree is a fragment, actually. Okay, so we operate on those fragments. You have this path between the nodes and subtrees that hang off from this path. We take the current fragment and we split it into smaller fragments. We do it in such a way that the depth of the recursion is log n, and the fragments of the recursion are always disjoint, so we can afford to go over all edges in the current fragment. Okay, so the fragments get smaller and smaller, but what about T2? We cannot afford to operate on the whole T2 in every step. Fortunately, we can play the same trick. So this is the current fragment. This is T2. And if you consider all cross edges connecting the current fragment with T2, Then again, you can think about the induced subtree of T2 and keep only the cheapest edge on each long path. So this allows us to define this compressed representation of the relevant part of T2, and its size is bounded by the number of cross edges with the left endpoint in the current fragment. So we will keep shrinking the fragments, and this will make also those compressed representation to get smaller and smaller. So the whole recursive step is as follows. We have a fragment f of T1 and a compressed representation of the relevant part of T2 of size O of S, where S is the number of cross edges with the left endpoint in F. Then for a constant number of edges E of the current fragment, we find the cheapest E prime by just looking at the whole compressed representation in O of S time. The remaining edges are partitioned into a constant number of fragments F1, F2, and so on. And for every Fi, we do the following. We take the current compressed representation, and in O of S time, we scan it and extract a compressed representation for the relevant part of the T2 for Fi. Okay, so we take the current representation and prepare the new representation. Finally, we recurse on Fi and this new compressed representation. We make sure that the depth is O of log n. I will not show you how, and then the running time becomes m log n. So I'm actually skipping some technicalities here. Actually, it's not enough to maintain one compressed representation. You need to keep track of two of them because depending on how the fragment looks like, you might need some extra information. So please see the paper for that. Okay, so to summarize, we show that the two-respecting problem can be solved deterministically in m log n time, and this gives us a solution for the minimum cut problem in m log² n time with high probability. So the only reason for the randomization is in the sampling step. Two obvious open questions are, is there a faster algorithm? So can we shave maybe another log? This doesn't seem to be easy. And also, is there a nil-linear time deterministic algorithm for the whole problem? We have such an algorithm for the unweighted case, but weights seem to be somehow difficult to deal with. So that's it, and thank you.